sigma squared. Okay, so that's like sigma squared. Okay, that's the population. Let's call it variance. Notice the word, I use the word pop for population, means only God knows it, right? And so then we take this like that, and we're going to square it, and we're going to divide by capital N, okay? And our best estimate for this is going to be this sample deviation. You know, so we can call it S squared, because this data is coming from what we've actually collected in the sample. And that one's equal to what? The summation from I equals 1 to what? Little n, right? Why? Because little n is the size of the sample. Size means the number of observations, yeah? And that one should make, this means add each observation. X sub I is an observation. And from every observation, we're going to subtract, the sample mean. Because that's sample mean, and we're going to square this because we don't want negative, right? So this is the best predictor of this, we're going to say, for now, right? Take our sample to get an estimate of the population variance. And of course we have mu, which I started with originally, but that's simply the summation of I equals 1 to capital N again, right? And you take every observation in your population, because you're going to go from 1 all the way to N, capital N, and you're going to divide that by capital N. So that's why I would use that here if I had what God knows. But I don't, so the next best estimate I'm going to have for this is going to be this guy here, right, which is X bar, which means our sample average, or mean. You know, it means the same as average. This is our sample deviation, or variance. Okay. Now, you can see if I want to take the square root, I would take square root of both sides, and then I'd get rid of this square, right? And they would call that a deviation, you know, when you see a square root. So this is equal to what? Well, this is the easiest of all. You take every observation, and starting from the first observation to the little n observation, and you divide that by, right, little n. You agree? You probably get sick of it after a while. But then there's this thing called a true or population distribution. Now, the distribution, depending on the thing, it could be a continuous distribution. What's continuous mean? Continuous means that I'm not going to lift my pen off when I'm drawing. Okay, that's a continuous. Whereas something like that, but would have discrete integers or whole numbers, would look like this. You know, where it's just a certain spot. This is just discrete. And we would tell what it is based on the kind of data we're collecting, whether it's coming from a process that just gives whole numbers, or is it a process that can take anything in between. But anyway, the shape is what we're really interested in, because once we know the shape, we know the kind of distribution, the phenomena the pattern's coming from. It's still random, but it's coming up with random out of this constraint. There is information to be culled out, right? And that information we can use to make predictions. So we don't normally have this because we can't plot every single point of the population. So we do what we call, you know, a histogram. Usually what you do is you're going to take certain cell width, right? And that cell width is something that you're going to determine that you need to do it so it's not too tight, not too big. But so basically you have the class width, right? I'm just going to call it the class width. And that's going to be your maximum observation minus your minimum observation divided by 2. Divided by the number of cells that you want. Okay? That would determine how wide these things are, so that they're uniformly that wide. Okay? Now, you're going to take a frequency, and so now you're going to go through your sample that you've selected now. Now you're going to look to see, okay, one fell here, another fell here, here, right? Another here, but 3 fell here, and let's say 5 here, and 5 here, right? And whatever, 1 there, okay? You can actually put this, you can put a count, obviously, right? 2, 3, let's see, 5, I don't know, 4, 1, right? Do you see that? Now, the reason when we count this, we're talking about a frequency. So this is called a frequency graph. Right, where we're just counting out how many things, right? So these are frequencies, the number of observations of frequency that fell into each cell, true? Now, if you take each one of this and you divide by n, n, remember, is the sample size, correct? Then, all of these numbers, if you divide by the total number, right, which would be 5 plus, you got 7, right? So let's say about 13, something like that. And my point is that that's your sample size, right? So if you divide every one of these by 13, can you see that no number will be greater than 1? Right? Because n is bigger than all of them, true? So once you turn those into a probability, then this would, like, you'd say 2 out of 13, whatever that would be. That would go like, then you can actually graph it, because on this thing, you can go from 0 to 1, because nothing's going to have 100% probability. Not yet, not this frequency thing, right? And when you figure out what this is, each cell's frequency is going to be whatever the number of the frequency is in that per cell, right? Divided by n. That's going to give you decimal. And then, of course, you know, if you got 3 here, this will be like whatever, you know. I'm just saying that this now is, okay, now we graphed it in terms of bars, right? But the summation of each one of these was in fact a probability. And the summation of all this better add up to 1. Right? Because we can't have anything, you know, either you fall into here or you don't. The sample size, the whole sample size fell into one of these cells. You don't have any extra one unless you have something called an outlier. And an outlier is when you have a freak data point that, you remember when I talked about a median? A median is that you could have like salaries, right? And you look at everybody's salary, but one guy is, you know, a pro football player or something. So his salary really puts everybody out in that town out of whack. So in that case, you wouldn't want to use the average. You want to use the median, because the median is the middle point. After you line them up in order, you come into the middle, right? That doesn't care how big this last number is, because you're coming in mechanically. But when you add it in here, it does affect the average. So one outlier could throw the whole thing out. So sometimes you look at it and go, oh, that's an outlier. I'm just throw that one out. Okay, it doesn't do it. Okay. So my point is that once you do this, it's no longer called a frequency graph. It's called, they call it a relative frequency. A relative frequency graph. It's the same thing, right? I just divided by n on each cell. Okay? Anybody? Yeah? Okay. So this is like a histogram then. It's really a graph of our relative frequency. Okay? Now, why do I bother with that? Because this is a thing that's going to give me an idea, right, of the true distribution that's really happening in the population. You see that? You sure? I don't know if you see it or not. I know I've done it over like 3 times, but I know it takes people a while to see what we're doing, because if you don't realize we're going to try to make predictions about this, this, and this, we may also make predictions of what they call R squared, which is going to be the correlation coefficient. That's, remember when we have a scatter plot? A scatter plot is when you have one variable here and another variable here, and you plot the points where they have in common, right? You would say, yeah, it looks like there's some correlation, right? It looks like what? Maybe R is positive correlation, right? Because that has a positive slope if you fit a line in it. So we would expect, you know, R squared to be greater than 0, because it's positive. It's such that it can't be greater than 1. So it's either, R is going to be, or R squared doesn't mean it's going to be less than or equal to 1. Okay? This gives you a measure. The sign gives you the direction, right? But the number R gives you how close it's clustered around that line. Okay? And I can show you the formula for that. I don't know if it's probably freak you out, but it might be nice to shock you every now and then. Let's see if they have the correlation coefficient. It's oh, yeah, it's on. Well, you don't have the. Do you have this table? No. Okay, I'll probably have it on the book. Anyway, it's I won't freak out yet with that. But it'd be hard. Now, it turns out that when you have a frequency, suppose you have, I give you this, all right? Can you go back to the original data? If I just gave you this, in terms of how many fell in there, can you convert this back to the original observations? Yeah, well, be careful, because these are falling between certain ranges, right? So I picked this with somewhat subjectively, right? So if I tell you 3 of them fell between here and here, you can't really go back and tell me exactly what the observations were, not in this case. Not unless you had the data to begin with, right? But I could give you just the frequency graph, which you could calculate your relative frequency graphs, right? But if I give you this, you can't really go back to the original data, but still it's worth it. So it turns out that you have another way of writing this then, the sample mean. Okay, we can write that as the summation of, now I'm going to go, this is just another way of writing the sample mean based off of a frequency, or I should say similar, because this is actually using the actual observation, right? And this one's using block frequencies, okay? So that's saying I can take this, right? Every frequency, f sub I. What's that mean? You're going to add every frequency in each cell, right? And I'm going to multiply it times x sub I. All right? And that's going to be divided by n. So this is a way to come up with an approximation of your sample mean, not by using this formula, but by using the frequency and the frequency and xi. Now, that brings a point. What are you going to use for xi? Well, we don't have the original points, right? So what we're using for xi is going to be the midpoint of every class cell. Okay? So if you find the midpoint of every class cell and figure out what the class, and then you take that number times this frequency plus. This means plus because I is going to go from 1 and stop at n. That's like a program, right? And so now you go here, frequency is 3. So if I just did this one here, for example, I would have something like the summation, right? And then I would have, well, if I wanted to extend it, like let's say I'm starting from here, I'm just going to write it out. So I start out with 1, right? With 1. So my first frequency, f sub 1, right, is going to be whatever, f is going to be, right, 2, correct? And this is going to be, let's say from, I don't know, I'm just going to do it from, I don't know what breaks to do. Let's say 5, 10, 15, 20, 25. Okay, so let's say it's going up units, it's basically units of 5. Now, you can put little gaps in here between there so that, you either fall in one cell or the other, because you might get an observation of 10 and you don't know which side to put it on. So you give a little error term on both sides so that, so for example, instead of going to 1 to 5, I might go to 1 to 4.99, right? And then gap and start over here at 5 so that I have a little gap here of 0.01. Do you see it? This helps sometimes to determine which, and this would go on to the next one, 4.999, or 9.999, see? So you might need to work a little gap in there, but the main point is that this, calculating this guy from the frequency graph, you're going to take 2, which is your 2 frequency point, right? In this case, the halfway point is going to be what? 2.5, correct? Then I had a frequency of, I'll put that 5, I'll say it got 3, right? And that's going to be times, well, we got 2.5, and now what do you have, 7.5? Correct? And you keep going that way till you get to the last one, which would be, like this would be 15, 20. So let's say 22 and a half. So you have a frequency of 1 times 22.5. And of course you have to divide that by the number of cells that you have going in there, or the total number of observations, which you know, right? It's just the sum of all your frequencies. And so you see we divide by n. It's a little weird. I just want to make sure that you know that there are two ways you can actually look at it, especially it depends how you've been handed the data. If you were handed the data and it's already grouped up, you would want to use this. But if you have the raw data, obviously this is better. Okay? And it's tied in with this relative histogram. Right? So to show you how it connects. But the main point, the big point, is that all of these guys are used to make estimates of what only God makes. So when we make predictions, we'll make it with a certain probability that this is a good chance that it represents this, what God knows, within a boundary, what we call our confidence interval. We'll actually put a confidence interval about what we think God's truth is. And we're saying we believe that there's an 80% chance, let's say, that this real truth is contained within this interval. Is that good? Okay. Now, these summations, I hope they're not freaking you out because it's just a counter, right? Every one of these can be extended. Like I can extend this to be, if I wanted to write it out, right? I write this summation thing out. Without the summation, I would just write x of 1 minus whatever the sample mean is, right? Squared. And that was when, because what did I do? I put 1 in here. You see where this little letter is? I put the 1 there. And I write it out. And I ask to myself, does 1 equal n? Well, not yet, because n is here is going to be like whatever our sample size is, right? If I haven't, then this thing says throw in a plus sign. Oh, okay. So now I go to the next thing. That's x sub 2 minus x bar. You see? Plus dot 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 plus. This will be the last term. It'll be x sub n minus x bar squared. All of that over n. Do you see? It's just a compact way of saying a summation. It is a summation. But in the mathematicians, they use this because they don't want to keep labeling it out. Suppose the n was 100. I don't want to keep going out. But that's what you'd have to do. You'd have to take each observation, subtract the sample mean, and square it. Take each observation, subtract it, and square it. And sum them. Okay? So that's exactly what this meant here when I did it for here, right? I started at 1, so here I have, well, here. Let me show you here how that looks here with this frequency graph. Okay, so what does this mean? If you extend it out, this means what? Well, I start with f sub 1, which would be the frequency on the first cell, times this, whatever this midpoint is going to be. I don't know how they indicate the midpoint there. Let's say. Well, they're just calling it x. Okay. So anyway, so this would be that midpoint. I don't know else how to do it. So it's midpoint. I don't know. This is the midpoint of each one of these. Okay. So this is like, I'm going to put x of mid 1, the first midpoint, plus, I haven't hit n yet, so I do the second one. And then I have x of the midpoint 2. And then plus, dot, 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 plus, and the last term is going to be fn, which is our last frequency in the last cell, right, times whatever the last midpoint was. You see? Now, that's all they are. They're just telling you. Now, the same thing here. Look at this. That's all it is. I'm just putting 1, and I don't stop this pattern. I don't stop this pattern until I hit n. Now, you'll see it in the book more like this. So, but in this case, if I take this, right, from I equals 1 to f sub I to n. Can somebody tell me what that's equal to? So what's it telling me is to add up my frequencies, isn't it? The frequency in this cell, this cell, this cell. So what should I add up to? What do you think? What does it add up to? It'd be what? Yeah, actually it ends up to be this, right? Because that's each one of these, if you sum them up, is your sample size. So you might see it written like this, but it's just, I don't know why they do it like that, but here's n. So now I have f of I, right, x, but instead of dividing by n, I'm going to divide by, well, you can do the sum of all the f's. The sum of all the f's is n, right? So that's just another form. Just so when you see it, you might need it. Or, yeah, I mean, that's it. The sum of, this is divided by the sum of everything, but this is another way of saying n. Right? Because you added up every single observation of all your frequencies. Is there any questions? Is it too easy? Okay. Oh, we can try to make it harder if you want. Unless it's just kidding. All right, so that's just another way of solving. I just want you to know, so when you have it in your repertoire, if you have frequency, you're going to have to use this kind of equation with the f's in them, okay? Now, it turns out that, okay, let's try this, because there's another equation for calculating this, right? And I assume there's going to be another equation to calculate it, but in terms of frequencies, correct? Wouldn't you think? Because we found two ways of doing the sample average. One is take the actual data and divide it by n. The other one is take the frequencies. Okay? So you would expect that there's going to be one for this, right? So let's try it. I'm not so concerned that you can really know how to manipulate summations, but that you know how to take it and actually solve it, spread it out, and do it. It's just a compact way. You might as well get used to it, because summations are what we use in almost every branch of mathematics, because it's a compact way of saying, sum them all up. Okay, so let me see. So if I go like this, so let me see. So now when we talked about the sample deviation variance, depends whether you have a square root or not, right? And we're talking about this is going to be our best estimator of what? R sigma squared, lowercase sigma squared, which is our deviation that only God knows. This is going to be our best predictor of that, we say. And we know that when we take the actual data, what is it? Well, you have to take each observation, right? Starting the counter from I equals 1 to little n, yes, the sample size, true? Is that okay? And then I'm going to subtract what? From each observation, I've already done this before, and I got this like this, so I have this as divided by n minus 1, right? Now, if you notice that n minus 1 has no counter on it, right? It's a fixed number. Do you see that? So if I had something like this, for example, suppose I had 3 times xi. That's a weird x, okay? And let's say I goes from 1 to n. You see this 3? What it really means is this. Is 3 times your first x of 1, right? It's not to n yet. So then I have 3 times x of 2, correct? And I'm just keep going like that, dot, 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 to my last term, which will be 3 to whatever the nth term is of the observation, the last observation, okay? Now, you can see that I can factor out a 3, can I? Right? And what do I have? Dot, dot, dot. Correct? So one of the properties of this thing is if you have a constant, you can factor it out. So I can call this is equal to 3. I brought it through the summation sign. You see it? Okay, and then all I have is this. So what I'm saying is a constant can be pulled out because it's the same term in each one, right? In this case, you're always going to have this n minus 1, right? But it's not affected by the summation. So you can write this as 1 over n minus 1 times the summation of x of I, x of r squared. I didn't do anything but pull this out because I don't need to keep repeating this under each term. No? Yeah? Okay. So, I don't know if you guys remember this thing where you have a minus b squared, right? Now, when we talk about powers, right, we talked about a particular power like this. You know, where it's a 2 in there. If it doesn't say, it's automatically considered a 2. But we said that is equivalent to this, correct? Do you remember? Okay, so too, if you have it like, you know, x. Okay, so now, and then you have to know that anything, if you make one copy of it, it's itself, right? Now, when you look at it like that, there's one rule that's sort of strange, but it's x to the 0. Does anybody know what that is? Yeah. It looks kind of weird, but let me show you how to think about powers. When I have this, and I put it on a copying machine on the platter, and if I put an x, and up here is where you put the number of copies that you want, correct? And then you push the power button, and it starts making copies of x. Cha-ching, cha-ching, cha-ching. That's all it is. It means multiply. That ching sound is the sound the machine's making every time it's pumping out a thing, right? Now, this machine's special because you can shove these 3 x's back in, and I'll put an x in there, and 3 will pop here. So it works the same way, okay? So what I'm saying is that if I have x cubed, that's all it means. That means I have 3 copies of x, right? So you can say I have 3 copies, correct? It's just, I'm saying it again, and backwards and forwards, called tautology. It's just circular thinking. All right, so what I want you to understand is if I have x cubed, right, times x squared, well, if we put this first one on the platter, we already know what that means. That's x times x times x, true? And this is x times x, correct? All multiplied together. So I can compact it and say, how many copies do I have of 1x? How many copies? 5 copies. So that's the general rule that I was telling you before, that x raised to the a times x raised to the b. They have to be the same x. I mean, the same base x is the same as x of a plus b. Okay? And the other one that I'd gone over is if you have x cubed, right? And you square that. All that means is that I have an x cubed already in here. I put that on the platter. Since I put that on the platter, I'm going to change this thing, of course, to 2, right? So I'm going to make 2 copies of that. That's cha-ching, cha-ching, correct? I'm telling it to make 2 copies of this whole thing. But I know that each one of these is copies too, so each one of these is going to be, right? How many copies of x do I have now? You want me to write it out bigger or what? I got 3 copies and another 3 copies. How many copies I got? 6 copies. So the end result is x to the, right? I had 3 copies, and then I make another copy of 3 copies, but each one of these is 3 copies, so that's 6, correct? So the rule of thumb is, look, that was multiplying. So when you have anything x to the a, and that's raised to the b, power to the power, that's going to be x to the a times b. Okay? Oh, that I know, it's just a refresher. So that's how I'm doing it. Why I do that? Because now I'm going to solve this problem. And what does this mean? This means 2 copies of what? A minus b, the whole packet, correct? Okay. So let me see. I'll just... Okay, so let's do that then. We'll bring it over here, and I'll have, let's say, a minus b, right? Cha-ching, cha-ching, because on the platter, right here, I'm going to put the whole thing A minus B. If you want, I'll put a parentheses. But this says I want 2 copies. 2 copies is cha-ching, cha-ching. Multiplied together, correct? All right, good. This is like your basic your algebra stuff. So now you use what I call this double horn thing, or what they call a foil. Do you see that that looks like a kind of like 2 horns? One's kind of freaky atrophied, one's small, one's bigger. You see it? You don't see it? It goes like this. Here's the bull. Huh? A claw? Yeah. It could be a pincher, like a lobster on the other side. This is actually a bull. Okay. Yeah, that's a good idea. Like a pincher? And then I could put a lobster. Anyway, I do that just to remind myself. So now, what is, let's go here. What is A times A? Well, that's going to be 2 copies of A, isn't it? Now, what is this? I have A times minus B. So that's minus AB. True? Anyway? So now, let's take the bottom part, B times A. Well, that's minus B times A, so that's another, and it doesn't matter if you write A times B or B times A, right, because it's commutative. 2 times 3 is the same as 3 times 2. So I can write this instead of B times A, I can write it times A times B. Do you see? Now I have a negative times a negative, which is a positive, 2 copies of B. This equals this, yes? Now I combine, I have 2 like animals. So I spent an AB and I spent another AB. I'm in the hole. I'm overdrawn 2 AB plus B squared. Does that remind you of anything before? The whole FOIL method, the whole, yeah. I don't know about the bull. He looks drunk. Okay, now, why am I doing that? Well, because I want to show you another form of calculating a sample deviation, right? And because it might be easier for you to calculate the other way. Now, luckily with the program, you can take the data over and pretty much hit a button and it's going to do it for you. But you need to work some by hand just to feel, like remember when I did the 80, 90, and 100? Just to kind of see it work. And you can do it again on this next way of handling it. Okay. So let's go back here. And so let's take a look at this. So if I have S squared for my sample deviation, right? S is what we did. And I have what I said before, right? You're going to take every observation from 1 to the nth. Well, that's a 1. That's an I equals 1 to little n. Yeah? And so I have to take every observation, and you want, what is variance? Somebody tell me what does variance mean? What do you think? What is variance? You don't know? This thing, what does it indicate as far as the distribution is concerned? You know what this is, right? Say again?
It gives you a little gray area to where it might be right from the left to the right.
You got to understand it's a measure. Yeah, it's a measure kind of. It's a measure of how tight this is. If I have a distribution, right? And this is my sample mean, correct? Let's say, and the histogram indicates that it looks like a bell curve. Yeah. So if I go up like this and I want to go out to see a measure of spread, that's going to be S, an S this way and S that way. So if your deviation is small, right, you would expect this to be pretty tight around the sample mean, yes? So you would expect that predictions in general are going to be better when the deviation is tight around the mean, right? As opposed to saying, like, we got data now that it looks more like, this. So now we got a lot bigger play here. So the deviation is a measure of the spread, sort of, around the average. Okay? Okay. So why? So notice that X bar is important to me. Because I'm going to take every observation and subtract it from the average. Every single observation I'm going to be subtracting the average from. So I get a measure of displacement to that observation. And I'm going to square it because sometimes, you know, your observation may be less than that and it'll come out a negative number. Are we okay with that? Okay, so then this is what? Well, it's divided minus 1. Now, if you recall, I did this a squared, sorry, scratch that. I did a minus b squared, right? And I went, and I did it, remember, and the first one term was a squared, and then I had minus 2ab, and then plus 2 copies of b, right? Well, I'm going to do that for here. Look what I'm going to do. I'm going to do this. X of I minus x bar, right, times x of I minus x bar. Why? Because it's 2 copies of this. Yeah? I told you put it on a copying machine, right? And I do the horn thing again, maybe a different color, so that look cooler. And then, okay, so in this case, this is an I, by the way. I'm just doing this part. I don't have the summation sign yet to it, okay? You all right with that? Okay, so what's x of I times x of I? X of I squared. You see it? Does anybody else know it? When I have x of I times x of I, how many copies of x of I do I have? Okay. Squared, correct? Now, this one is minus, right? I'm going this way, x of I, that's this guy, times x bar. Is okay? And now I'm going to do this one. Well, that's minus again. Here doesn't require an average. There is no x bar anymore. So you might want to take every observation and square it, and then take the sum of each of all the observations. So let's try it. Let's do an example. See if it works. So I'm over here, and I'm going to try the same thing, the 3 scores. Okay, so let's try an actual example now. And so let's do the 3 scores. So I have 80, 90, all right, and 100. And I will assign this as x of 1, x of 2, and x of 3. That's the name. I'm just calling them a name. It's not 2 to the 2 power. Is this okay? All right. So let's talk about this. The sum of xi squared. From I equals 1 to 3. So what does this mean? This means I got to take 80 squared plus 90 squared plus 100 squared. After I do that, then I have to figure out this guy. Notice how I squared each one. By the way, you know, I'm going to have a... Okay, well, anyway, that's that observation. Now, let's do this one. I equals 1, 2. Now, watch, be careful, because this is x of I, right? But it's just quantity, this whole thing squared. 2 copies of that, right? So what does it mean? Well, let's just expand what this guy means, right? It means x of 1 plus x of 2 plus x of 3, yeah? Whatever that quantity is squared. In this case, we're going to have what? 80 plus 90 plus 100. Correct? So what, we got like 270, right? Okay, so that's going to be, so this is going to be end up being, whatever this is going to be 270 quantity squared. All right? So now we can plug in our values. So s squared is going to be equal to, you know, whatever this is equal to. I don't know if somebody wants to do that. Let's see. Does anybody have a calculator? You can do it fast, or I'll do it. Whatever. I'm just filling in the blanks, because now I know what this is, right? I did it. I'm calculating what it is now. Anybody got it? Is working on it? Okay, 88. Okay. Huh? It's 60. Yeah, 80 times 80. So that 8 times 8 is 64, right? And 2 zeros. 9 times 9 is 81. And 2 zeros, right? And that's going to be what? That's going to be twice. So that's going to be 4 zeros, right? So I should be getting what? Let's see, 0, 0, 5, 14. Something like that. Okay? And what do I have here? What's n equal to? That's right. So 3 times 24,500. I don't know if that's right. I just did it. Correct? Minus, I don't know where that came from. Minus what? 270, correct? That's what this is. It's just adding them all up, right? Minus 270 squared. And that's going to be over, what's n? 3. And what's this? It's 3 minus 1. Okay? And that should calculate your deviation as squared. Now, if it wants a variance, you're going to take the square root of both sides. So it's going to be the square root of all that. Okay? How did it look up here? Well, it looked easier because once you got to know what your average is. So you have to calculate your average first, right? In our case, it's 90, isn't it? Our average of this. So, if I write it out this way, it looks easier. I mean, you got the first observation is what's 80 minus 90. You see that would be negative, right? You have 80, but you spent 90, right? Would you see that's a negative number? Negative 10, yes? But I'm not worried about it because I squared it. Plus 90 minus 90, that's squared, but that's just 0, right? Plus, and then the last one is what? It's going to be what? The last one is what, 100? Minus 90 squared, right? All of that's going to be divided by n, which is 3 minus 1, which is 2. Okay. So if you're so inclined, those two numbers should come out the same. It's just a different way of writing it. Okay? So now when you look at your formulas, you'll be able to see 4 formulas or 5, and many of them are just the same way of doing this, but in another form of the same thing. Okay, so let me clean that up. So let's clean it up and get it neater here. Okay, so starting with mu from the population, we know that that's a summation of I equals 1 to capital N of every observation in the population divided by n. True? That's what it is. That's my sample. No, not my sample, my population mean. My population mean. And mean means average. Okay? Now, the only way that we know how to write this one is the summation of, xi. Just, what it is. I don't know how. Well, okay, there's one other way to write it. What way is that? The other way to write it was if it happens to come from a frequency. Do you remember? If it was a frequency graph? Does anybody remember that? Yeah, so remember. Yeah.
Summation of fi.
Yes. So that was the summation of
f sub I.
f of sub I.
And then x sub I.
And then x sub I.
Yes.
Okay, so fi and then x sub I. Divided by, this looks kind of weird, but this f of I. Now, remember what fi is? That ends up equaling n. So there are 2 ways we can represent. Okay, now this is actually equal to s, right? S, let's say s, or I mean the sample mean, right? So this is x bar. That's what we got from our sample. This is for the population. Am I square with that? Everybody got it now? This is x bar. Weird looking x bar. You get it? Which is our best predictor of this. But there's another way of writing this guy. You can write it in terms of frequency. Okay? Yes or no? Okay, now the next one is this guy. This is our population variance. So, or, see, there's a difference. The only difference between population variance and deviation is whether you take the square root or not. And this one that we know from the population is going to be the summation of every observation in the population minus something we don't really know, mu, because it's a very large population, right? And of course, I'm going to subtract that by, I'm going to subtract the average from the population average, right? I'm going to square it, and I'm going to divide by, okay? Notice that that is all using these guys here. These guys, this and this, they're called what? They're parameters. But x bar and what we're going to use now, s squared, those are sample statistics. It's all about vocabulary. So we're using our sample statistics to make inferences about the population parameters. You got it? We're trying to figure out these parameters, right? And we're using a best guess of it by using our sample statistics. And in this case, one of them is x barred, another one is the standard sample deviation, and another one that we'll use is like a histogram, but basically that's to give us the true population distribution. Is it sinking in, or am I boring you to death? Anyway, this one can be written as this, right? Now I'm going to take, every observation, and I'm going to subtract what from every observation? The sample mean. If you look over here, I didn't subtract the sample mean, I subtract the population mean. Okay, so x, and then I'm going to subtract x bar, yes? You see it looks a lot like this one, right? And then I'm going to divide that times n minus 1, okay? And then we went over another way of rewriting this depending on how your data is. Okay, you can write it like this. You take the summation of x of I. Notice where my parentheses is. This, what is this saying? It's saying that you have to square every observation before you add the next term. That's why it's in parentheses. You're squaring each individual observation before you're adding it, right? Which is different than if you take, well, in this case, n, and so we're going to take the summation of x of I. Oh, sorry, I got that wrong. Let me get this, sorry. Let me go here. I don't want my n there. Okay, so what I'm saying is that you can take this guy here, right, and this is going to be, okay, so this is going to be the summation. Look at the difference. And this is going to be x sub I in brackets squared. Do you see the difference? This is telling you add up all the norm, and when you get the total, then square it. No? Or yeah? Okay, and that can be, you multiply this times n, and this is over n minus 1. So these are the two forms that you can have it. Is there another form? Yeah, there's another form, because remember another way of writing the sample mean is in terms of frequency. So you can replace this x bar by not this one, but if you happen to have data in terms of frequency, then I could substitute this guy in, right? So we can write that as, okay, so what I'm going to do is that each one of those, so I can rewrite this if I have frequency. I'm going to write this as n, right, times the summation of f sub I, x sub I squared, plus over here, and I'm going to have, do I have plus? No, I have minus over here. Let's see. Yeah. Okay, up here, let's go right here. Let me take this guy. This is my bad. This is subtract. Okay? So basically, I'm going to rewrite that. So I just put f of I times x of I, because I'm not frequency. Remember what these are now? These are not our regular x of i's. They're like midpoints of the cells. Okay, so it's like x of mi. I'm just so you know, it's not exactly the observation anymore, because you're getting information off the frequency chart. So how about what's next? Well, on that one, then we have minus, and then we have n times, and then what they're going to put there is going to be the same thing. Okay, so here I'm going to have the summation of f of I times x of I, this quantity squared, right? And that's going to all be divided by, this part here is going to be same thing, n times n minus 1. Now, how can I rewrite n? You know, n is equal to the summation of all the frequencies from I equals 1 to n, so you can put it in terms of FIs if you want. Any questions? Those you'll be using over and over, and when you do get a chance to look at the table, I can show you on the book. I just went over this chunk here of the tendencies, what we call it descriptive statistics. All right? So, now, let's take a look at the book for a second here at one of the homework problems. So we can try to solve some of those. So, let's see if I go here. Oh, wait, I got to get out. Okay. So, oh, that's nice. I don't want it to disconnect. Let's see. Okay. So, is it? Oh, it's completely disconnected, isn't it? Huh?
Said it connected again.
Oh, it did? It must have known I was looking. Okay, so. Okay, so I'm going to go in. I don't want it now. And yeah, what the hell? Okay, and then I'm going to sign in, and then sign in again. Okay, whereabouts are you now? At 2 something, or where are you? And most of you in the homework. 2. Okay. So let's take a look at this. Okay. I just did it, so why didn't it do that? Oh, it's probably still working on it. There we go. Okay. So, let me see if I can go over here. Okay. So, how do I get into 2.4? Okay. So, let me go back here. Okay, I went through this before. So, let's see. I don't know if you're 2.1, 2.2, anybody? Okay, this one's about histograms. Okay, and remember here where I call it frequency distribution, and then relative frequency distribution, which is your histogram, right? And then you have the basic concepts of this, but see if it'll let me preview it. I remember last time I saw it like a student or something. Okay.
Yeah, just click on question.
Yeah. Let me take a look here. Okay. Well, anyway, the population ages of inaugurations of U.S. presidents. It's a bit small, right? The data size, the sample size, it's going to be hard to make a frequency, a graph and you only have, what, five points? So that's a problem. Let me see, I'm trying to get here. Okay, if we collect blood platelets counts, and if our sample size has a single outlier, that means you have an alien cell in there. How will the outlier appear in the histogram? It could really screw things up, because if you're going to, you remember during the class size, by taking the maximum minus the minimum, divided by how many cells you want, right? Yes? So if one of them is way, way out there, by the time you do your histogram, you're going to have all your frequencies here and then a gap, and then one little blip over here, right? So you might want to remove it when you're trying to get an idea of what the real distribution coming from. Okay? Let's go over here. Okay, so here. Now, do you see these numbers? So you can tell right off by looking at this is not a relative frequency, right? These are not probabilities. These are just counts. So between 0 and 130, the midpoint, I don't know whether they're using 110 there, 130. So they say they have 3 observations fell in there. Do you see that? So how many members are included in the histogram? Well, they're basically asking the sample size, aren't they? In a way. So what are you going to do? Well, you got 3 here, 1 here, right? 2 here. And you're going to add them up, correct? So that should be next. Now, let me see if this has it. I don't know if this one, this probably doesn't because there's no, oh yeah, it does. So this is kind of cool because when you do that, right, you can say, view an example. Or you can say, open the textbook. Or if I want to do some kind of actually make it, I can go stat crunch. Okay? Or last resort, you can ask me. No, just kidding. But you can print it out and bring it to class if you don't get that problem, right? So let's see. Let's take a look and see how that looks like. Okay. Now, see, so now it's working you through it. Okay, so there are 4 parts here. So it says histogram. I'm not sure what they're doing here. Oh, it's just, yeah. So it's somewhat similar, right? Jason are drawing without graphs. So this is why I kind of like this, because if you get stuck, how can you beat that? Sample size can be by adding the heights of the bars of each histogram. Didn't I just say that? Yeah. So okay, so right here it would be what? This is pretty easy. Does it go down any further? No. Okay, so you just add them up, right? So let's see. That's 10. And this is 17. 19? I don't know if we got that. Oh, yeah. Look at that. That's like psychic. Okay. Anyway, I think you can get the idea of the advantage of this. It's one thing to take it online, but you have an instructor too. Well, it's still a frequency ground. But, okay, so this is your body mass. Okay, it's a ratio, something to do with, figuring out if you're obese or not. And so they're going to have a lower class. You see where the low class is? Starting at 15, right? Because there's nothing smaller here than 15, correct? Somebody say yeah. Yeah? Okay, so let's try it. So I'm going to go here. And I'm going to go this. Now that's pretty cool because it's transferring all your data. Otherwise, you have to do it on your calculator. Okay, now there it is, Bob. How can you beat that? It's like being spoon-fed. And then, what do we want to do, a graph? And what kind of one do we want? I guess the histogram. I don't know. That's after you divide by n. I don't know. So this one you have to put it over there. See it? And then you remember where we were starting at? 15. Yep. and then, and then you remember the width? It was in the back. I don't know if I can. 6. So is it? Where is it down here? Now, remember that I tell you that the histograms is kind of give you an idea of what the true distribution is. You can overlay a distribution on top of your histogram, right? Like you can pick whether you think it's a bell curve, a beta, a chi, exponential. These are different distributions, an F and T. So it can try to overlay it. This, you could say, yeah. You understand what I'm saying? Okay, let's just see. I don't know what this is going to compute. Okay, so that's nice. Isn't that easier to do it this way? I don't know, but I mean, you're welcome to. What do you think? Isn't that cool? And then it's going to help us with all our predictions and everything. It does a lot of work. So if you don't have it, it's going to be more work is all I'm saying. Okay. Anyway, that's what I wanted to show you. All right. Yeah, you're just right. Or just hand them in when you're ready. Because I'm going to just check them, make sure they're done.
Okay.
Yeah. Anything else?
I am having a hard time with what you're talking about because you're not showing
An example?
examples. So it's just hard.
Right. Well, I did that 80-90 thing, yeah. But I didn't really do an example so much with the frequency.
Yeah.
But I can do that.
Okay.
But, it's kind of on you. You need to ask me something.
I know. I'm really shy and I haven't been in a math class for like 4 or 5 years now.
Yeah.